Hello, ladies and gentlemen, Root Beer here, and I'm going to be finishing off the 2012 Euclid Math Contest. We're on the very last question, question number 10. So, here's the question. If you haven't tried it already, please do give it a shot. Pause the video. I promise I won't be offended. I'll be here waiting for you to unpause, and then we can come back and you can compare your solution to mine, or if you didn't get that far, you can take a look at, or you can take a listen to how I'm processing things, and maybe pick up a tip or two for your next Euclid. But question 10 here. For each positive integer n, an Eden sequence from 1, 2, 3 all the way up to n is defined to be a sequence that satisfies the following conditions. Each of its terms is an element from 1, 2, 3, 4, 5 all the way up to n. The sequence is increasing. And finally, the terms in odd-numbered positions are odd. The terms in even-numbered positions are even. So already, incidentally, just before I finish this off, I feel like you could very, very nicely perhaps generalize Eden sequences. This is clearly working with odds and evens, but you could have modulo 3, and then the positions in 0 mod 3 are 0 mod 3 and 1 mod 3. I think that would be a very nifty maybe extension to this problem. But I haven't finished reading this. I like this because I feel like I could make a similar question that's just a bit more general, and I like doing that. Anyway, for example, the 4 Eden sequences from 1, 2, 3 are 1, 3, 1, 2, and 1, 2, 3. Okay, so you'll notice odd, then even, odd, even, odd, and these two are just plain odd. Alright, so A, determine the number of Eden sequences from 1, 2, 3, 4, 5. And B, for each positive integer n, let En be the number of Eden sequences from 1, 2, 3, 4, 5 all the way up to n. If E17 is 4,180 and E20 is 17,710, determine E18 and E19. So they're doing some computation work there for us in B. And the reason I'm reading B, usually for question 10, they introduce a brand new concept and ask you to do this, that, and the other thing with this brand new concept. So it's a good idea to read 10 all together. But the fact that they're asking me for 18 and 19, and they're giving me some values, suggests to me that perhaps it's quite hard to figure out En, but that maybe if you're given a similar En, that there's some generalization. So, for example, I don't think it'll be this easy, but E17. So these are all Eden sequences that come from 1, 2, 3, 4, 5, 6, 7, all the way up to 17. E19, could we just come in and add 19 to the end of all the sequences for 17? Now I know what you're thinking. No, because if it's an odd-length sequence, you can't just add on a 19. But you could add on an 18 and 19. So maybe all the even sequences from 17, you could add on a 19 for free. And then it becomes an odd sequence, or an odd length sequence for E19. And if it's an odd length sequence for 17, you can come along and add on 18, 19, and then it becomes another odd length sequence. Okay. But that's what I'm trying to get at, is that maybe there's a way to use 17 to determine 19. Like maybe E19 is twice E17. Maybe there's a general rule that En is always 2 times En minus 2, because you lose both an odd and an even number. Maybe it's special that way. And then from E20 we can work back to E18, something like that. That's just what's going on in my mind. So I'm starting to think recursion. And with that in mind, I'm going to go back to A now and try to work out the answer to A. Just, can I work out all the Eden sequences for 1, 2, 3, 4, 5? But I'm going to try and keep my eye on how I'm making these sequences. Am I noticing some sort of recursion? Can I figure out some patterns? Okay, that's how I'm approaching this one. Okay, but let's just get a few marks for free with the Eden sequences for 1, 2, 3, 4. So, what's the best way to be organized about this? Let's say sequences of length 1. Well, it's got to just be an odd one, so it's either 1, 3, or 5. Sequences of length 2. So you have to start with something odd, and then follow it with something even. So we could start with 1 and then follow it with 2, 1 and follow it with 4. Or I could start it with 3 and follow it before, but I can't start anything with 5 because there isn't a further even number to be my second term. Sequences of length 3, so 1, 2, 3 would work. In fact, 1, 2, 5 would also work because 5 is an odd number after 2. We could have 1, 4, 5. Or we could have 3, 4, 5. And actually, what I'm noticing is, for some of these, I'm just appending 5 on. So there's some sort of recursion, because every one of these even sequences, it didn't matter whether or not we were working with 1, 2, 3, 4 or 1, 2, 3, 4, 5, because 5 doesn't make an appearance. Length 4, 1, 2, 3, 4. I think that's going to be it, because you have to have the 2 even numbers in the even positions. There's only 2 even numbers. So 4 has to go here, 2 has to go here, and that fills in 1 and 3 for the rest. And then just one sequence of length 5. So I think that's it. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I guess to use their notation in part B, oops, E5 is 12. E5 is 12. Okay. But it looks like... So an observation I'm going to make, if n is odd, and we got, say, A1, A2, A2k is an even sequence, clearly of even length, coming from 1 to all the way up to n minus 1, then A1, A2, all the way up to AK, and then add on n is an odd length even sequence from 1, 2, 3, all the way up to n. And you can do the same sort of thing with an odd, if you start with an odd length sequence and tack on an even number. So if you've got an odd length sequence, from the first numbers other than the n you're talking about. So there is this nice recursion almost. But it seems to only be working if n is odd and I take an even length sequence. If n is even and I take an odd length sequence. Another thing I can make, because we did this with 5, if n is odd, n is an odd length sequence. But the same is not true if n is even. If n is even, I can't just stick that number there. 2 is not a good sequence. So there's something special that happens if n is odd. You get this sort of extra little bit. Now, if n is odd, what can an even length sequence coming from 1, 2, 3, 4, 5, because I know what an odd length sequence could look like. It could look like a smaller even sequence. Yeah. I'm thinking. So here's what I want to say. Suppose n is odd. and A1, A2, AK is an even sequence. And we'll say, I'm just gonna say from n instead of 1, 2, 3 all the way up to n. In fact, did they have a name for it? No, they say an even sequence. I'm just gonna say the last number, if that's all right with you guys. So if n is odd, then if k is even, AK is even, and so AK is less than n because n is odd. So A1, A2, AK is an even sequence from n minus 1. So I can count it as a sequence coming from the previous even number. So then if k is odd, we have some more possibilities. So k could be 1, and then AK being equal to n would be interesting. K is greater than 1 if AK is n, then A1, A2, if I take off the previous thing, so take off this n, this is an even length. I was wanting to write this all on the same page, but we'll say it's an even length sequence from the previous terms. Or perhaps k is greater than 1 and AK is not n. Then A1, A2, all the way up to AK is an odd length sequence from n minus 1. So if I've got an even length sequence coming from 1, 2, all the way up to n, if it's even, then I know it must just be a duplicate even sequence from the previous value of capital N. If you're looking at an odd sequence, you have more possibilities. It could just be n itself. Or it could end in n, and then the first bit is an even length sequence coming from n minus 1. Or it could be an odd length sequence that doesn't end with n, in which case then it's an odd length sequence from n minus 1. Now, if n is even, we should get this almost the exact same thing, but we shouldn't get this case here. It should be everything else, maybe flipping evens and odds. But I feel like we're zooming in on a recurrence. So if this is an even sequence for n, I said. And then if k is, so the first one we did was even, so if it's an odd length sequence, AK is odd, so AK can't be n, so AK has to be less than n. So A1 through A2 all the way up to k, AK is odd, is an odd sequence from 1 up to n minus 1. Almost the exact same thing. So this part here, same thing as this part here. Basically, if the parity of the length of your sequence doesn't match up with your capital N, you must be a sequence from a previous n. And now if you're even, if k is even, then we have only two possibilities. Because you can't get k equals 1. K has to be at least 2. So if AK is n, then take away that term, And then you get an odd length sequence from the previous terms. If AK is not n, then A1 through A2 through AK is an even length sequence from n minus 1. Because I don't use n, so I must only be using numbers less than capital N. Okay, so here's my plan. Oh, they used E already, didn't they? Yeah, they're already using E. I'll say even, V for even, D for odd. So let Vn equal the number of even length Eden sequences from n. I'm going to let Dn be the number of odd length sequences from n. So our previous work should tell me that if n is odd, Vn should just be, I should just copy the previous even length Eden sequences. Dn, it's going to be 1 for that single case where it's just a sequence that is n. Then sequences of even length from before and sequences of odd length from before. So Dn minus 1, Vn minus 1. If n is even, then the odd sequences are just copied from before. And the even length sequences are either odd length sequences that I added on to, or were already even length sequences that don't involve n. So this gives me a nice recursion relationship where I can actually, and then, so hold on, so I've got a theory. You can see I've developed a recursion. What I'm going to do is I'm going to use the 3 that they give us, 5, I might even compute 4 just to make sure the even stuff is on point. But I feel like we can actually just get the answers directly. I don't have to develop some recursion involving immediately previous things. There might be a better way. There might be a way to combine this stuff. But what was I going to say? So I want to test this out. I want to make sure this works. This is for me. This is not something I would necessarily have to write up, although I could say, here's an example if I thought my recursion or my explanation was unclear. But what I want to do is I want to test things out. So I'm going to say there are 0 length 1 even sequences. And there's if I just have the sequence of length 1, then there's 1 odd length sequence, or odd length 1 sequence. And then, so V2 should be add up the previous 2, and D2 should just be copy the previous one. And now V3 is odd, so copy the previous one. D3 should be 1 plus the previous 2, 1 and 1. So 3. And then V4, add up the previous line, so 1 plus 3 is 4. D4, just copy the previous one. D5, add up the previous 2 and add on a 1 for the just write out sequence 5. V5, copy the previous even sequences, because having an extra 5 does nothing. So, this is looking good. Now, if I go to their sequences, they have 1 of even length and 3 of odd length, exactly as I predict. And now we should get 4 of even length back here with 5. 1, 2, 3, 4. And so the remaining 8 must be odd length, and they are. So this is really working. So I guess we could just keep doing this. Evens, you copy the previous one and add up those, and V7. Copy previous two and add once at 21. So yeah, this could work out quite nicely. If I get this, I'm going to also try and explore how to get their, maybe get it a little faster with their stuff. But I've got something that works. It's, you know, it's up to you whether or not you want to keep going and try to, it'll be 33, get something that might work a little faster. There's no harm in that. You just don't want to waste too much time trying to get something that works a little faster. I'm also going to bust out my calculator now to try and make this go a little faster. This should be 55. And then when I get to 17, which I will in a moment, I should be able to check to make sure that my answer looks the same as their answer. But the numbers are increasing a fair bit. So V11, copy that number. D11, 88 plus 55 plus 1, 144. Actually, I'm noticing something else here. These are all Fibonacci numbers. It's every other Fibonacci number. And these numbers are a Fibonacci number minus 1. It's the missing Fibonacci number minus 1. I wonder if there's a way to connect that. There's definitely some more going on here, but I want to get my answer here. And I'm already up to the 12, so we'll say 144 plus 88, 232. Then I add on 144 and add 1 for 377. Then I add on 232. 609. 609 plus 377 plus 1. Oops, almost forgot that. 987, and I do recognize that. That is still a Fibonacci number, although I don't remember which one it is off the top of my head. But we're starting to venture into territory that I am not as familiar with in terms of Fibonacci numbers. 1596. And then D16 should be the previous one, which was 987. And then, okay, here now I can test what I've got going on. Add on 987 and then add on 1. 2584. I'm just going to keep going, but I am going to verify that this line adds up to what I want. And the 20 adds up to what I want as well. So V18 should add on 1596, and we get 4,180. 19, copy the same number, add on 2584, and add on 1. 6765. And then add on 4180. 10,945. So let's just quickly add up the 17 and 20 lines to make sure I haven't made an arithmetic mistake somewhere, maybe forgotten to add on a 1 somewhere. 1596 plus 2,584. 4180. I feel like that was a number they gave us. And then 10,954 plus 6,765. 17. It definitely started 17 something. So are these correct? Yes and yes. So I think we've got it. Just had to work out these sequences. So we'll say 4180 plus... Oh, incidentally, this number is the previous one. Well, actually, no, that makes sense, because that's how we obtain them. We add them up. Plus 2584. So we should be looking at 6764. That's E18. And we have the method written down to prove it. And then the next one, 4180 plus 6765. 1945. And that should be E19. Okay. Now, in terms of these things looking like Fibonacci numbers, which they really, really do, I mean, the D's here look very much like Fibonacci numbers. And is there a faster way to do that? Is there a way to say, oh, I know this one and I know this one? Well, maybe we sort of jumped off, or used this as sort of a jumping off point too early. So if I return to these, by the way, I'm done. Like, subscribe, whatever. I just want to investigate this more. Okay, it's been a wonderful contest, but let's investigate this a bit more. Okay. So if n is odd, I'm just gonna copy down what I had. And if n is even, then I'll have Vn is Vn minus 1 plus Dn minus 1, and Dn is just the previous Dn minus 1. So, what can we do? So for any n, Vn is Vn minus 1. So if n is odd, Vn is Vn minus 1. But now this is even. So I can break it down as to Vn minus 2 plus Dn minus 2. If n is even, then Vn is Vn minus 1 plus Dn minus 1. But this is odd, so then it's just the previous Vn. And this is odd, so it's some other stuff. I was really hoping that there'd be some sort of recursion. Well, maybe if we add them up. Or maybe there isn't, or maybe there is and I'm just not smart enough to see it. That can happen. So En is Vn plus Dn. If n is odd, En, so the Vn can be written as Vn minus 1. And then we get 1 Dn minus 1 plus Vn minus 1. Which, I mean, this is En minus 1. And then this Vn, because this is now even, it splits up as Vn minus 2 plus Dn minus 2. Which is just, yeah, so here's what I should have written a while ago. I should have said that this is just En minus 1, and this is En minus 1 for that as well. So this nice recurrence relation holds, and now all I need to know is some previous ENs, two previous ENs. If n is even, En is Vn plus Dn, but now the Vn can turn into the previous En minus 1, and the Dn turns into Dn minus 1, which turns into 1 plus the previous Alright, so for both cases, we get the same recurrence. So you get en minus 1 plus 1 plus en minus 2. And I suspect that would probably be a very good way to go about doing it. There might be a more direct way to see it. I'm happy with the way I did it. I built it up with odd and even sequences. There might be another way to do it. You know, I found that way pretty quickly, I would say. So I didn't really entertain other possibilities, but I'm sure there's a nice justification for this particular sequence. But let's see if we realized this, if this is better for working things out. So then that would mean E20, which I know. They said it was 17,710, I think, is E20. I can change that to E19 plus E18, both of which I don't know, plus 1. But then this E19 can turn into E18 plus E17 plus 1. And I do know E17. So I get 2 E18s plus 2 plus E17, which they said was 4,000 something? 4,180. So I can work out 2 E18, 17,710 minus 4,182. I'll just grab my calculator there. 7,710 minus 4,182. Divide by 2. And look at that. 6,764, which I think is what we had previously. Yes, it was. And then from there, I can use this to work it out. So E19 is 17,710. So this is probably the way you were meant to do it. You're meant to find this recursion. So 17,710 minus 6,764 minus another 1. And look at that, 10,945. Or 10,945. Okay. So again, very nice. Blah, blah, blah. We're done. You're more than welcome to go. I wouldn't blame you if you shut it off by now. But I really like this Eden sequence. I'm feeling good. I'm feeling like, I'm just happy. It's a good question. So I want to spend a little bit of time, and I thought I'd share it with you because I got time, exploring the sort of idea that jumped into my head when I first saw the Eden sequences. There's nothing special about odd and even. But, so, here's what we're going to do. What's a fancy term for, let's say an M Eden sequence from 1, 2, 3, all the way up to N is increasing, only uses these numbers, and here's the new thing. So I'll say is a sequence A1, A2, all the way up to AK. So I'm saying they're increasing. I'll say they're between 1 and N. And then my final condition is A, MT plus R is, well, because I'm just playing around with this on my own, I'm going to use the fancy notation. So I will say AI is congruent to I mod M. All I'm saying is the term place and the term itself have the same remainder when you divide through by M. So the Eden sequences from this question are really just two Eden sequences. And a one Eden sequence is just any old Eden sequence. Okay. So I think we can use this same idea of recursion that I was working with and say something to the effect of, let's say U, I, M equal the number, let's say capital N, number of Eden sequences, m Eden sequences, from n of length equivalent to I mod m. So from before, Vn would be U0n, and Dn would be U1n. That's all I'm saying. So now I'm separating these things out. So I'm pretty sure if n is congruent to 1 mod m, you'll get one extra sequence of length n. But other than that, you'll get U1n is 1 plus all the other previous... Well, actually, now that I've got... let's let all the Eden sequences... This will just be the sum of them all. So this is something I didn't do earlier, which I should have. Okay, so that's the number of Eden, m Eden sequences, period. Then U1n will be 1 plus... because 1 is congruent to 1 mod n, and then it'll be all the previous sequences. And then any other sequence is just you wouldn't get anything new by tacking on n at the end. Right? I feel like perhaps I'm going too fast. I've got ideas jumping into my head, although at this point I'm starting to write down symbols and equations that I don't have justified even to myself, let alone on paper so far. I think I'm trying to jump to a generalization when maybe I should work mod 3 for a moment. Well, first I'm gonna write down what I think it is. Okay, so here's what I think it is. UIN is equal to exactly one of the following. 1 plus En minus 1 if n is congruent to I is congruent to 1 mod n. Any of the previous ones if I is congruent to n mod m, but it's different than 1. And then just your previous term, or the previous thing, n minus 1, if I is not congruent to n. So I think that covers what we had earlier quite nicely. Do I believe it, though? And if I do, then what does this mean for any sort of recursion that I could have? Am I going to get some sort of generalized Fibonacci number happening? Yes, actually, I will. So if this holds true, then En is U0n plus U1n plus UM minus 1n. N will be congruent to one of these. Let's say it's this last one. And then all the previous ones will, because n's not congruent to them, be equal to their smaller copies. I'm going to add in a little bit more here. So that'll be equal to the previous one, according to this rule. And then each of these goes down by 1. But now, since n has gone down by 1, next time this will be equal to the previous un minus 2. Or, sorry, en minus 2. And it'll keep going down. Now, this one will eventually turn into e whatever, and then it'll always give a plus 1 no matter where you are. And this one also eventually turn into an e something or other. So, oh, these should all have m's. So what we can definitely say is it's 1 plus em n minus 1, em n minus 2, and I'm going to go down, based on our work with m equals 2, all the way down to em n minus m. And so we get a nice little recursion formula. And there we go. That should be it. Now, I think I'd like to test this out. So I think the last thing I'm going to do in this video, and then I'll do a proper wrap-up, is I want to test this out for, say, m equals 3. Just something pretty basic. We'll compute a few of these. So if m is 3, still when n is 1, you're going to only get the one sequence. When n is 2, well, you could get one sequence there or another sequence there with 1, 2. With 3, you'll get 1, 1, 2, or 1, 2, 3, and that's it. You can't get any other sort of order there. But now with n equals 4, what would my theory predict? 1, 2, 3. So 1, 2, 3 plus 1, so it should be 7. There should be 7 possibilities with n is 4. 1. 4, obviously. 1, 2. 1, 2, 3. Not what I was expecting. So something has gone a little off, let's say. What did I do wrong? What could I do better? Well, I'm confident this follows from this, so maybe I'm wrong here. I definitely think n equals 4 is correct. And let's see, counting the mod 1 length sequences, there's 1, 1, 1, and now there's finally 2 of them. Counting the mod 2 length sequences, 1, 2, it's another one of them. And then counting the mod 3 length sequences. So n equals 5, how many of them are there? Well, there's 1, there's 4, those are the ones of length 1. For length 2, you have to start with a 1 or a 4. For length... Oh! I didn't get this length 4 sequence. So there's another one, I guess. So it's 5. But 5 is not what I was expecting. I was expecting 7. Length 3 sequences. Well, you can have 1, 2, 3. 1, then 5 is not going to work. 4, then 5 is not going to work. So you got to have 1, 2, 3. 3 is the only multiple of 3, so it's got to go in that position. 1, 2, 3, 4. And then 1, 2, 3, 4, 5 is the only length 5 sequence. So we got 3. We got 2 more of those. The same number of those. And oh, so we got 1 more of those. 3 more of those. Interesting. 1, 2, 3, 4, 5, 6, 7, 8 of them. 5 of them here, 3 of them here, 2 of them here, 1 of them here. Fibonacci numbers again. But why didn't my previous calculations work? So this number stayed the same. The red one stayed the same 3 times, and then it jumped up by 2. And then the blue one stayed the same 3 times and jumped up by 3. Why did it jump up by 3 and not, say, 4? Alright, let's do N6. And then I might just leave this to you guys to fix. I sped through it. I don't think I properly justified everything, but let's see. 1 or 4. That's the only way to start with length 2 or length 1. So you could have 1, 2, 1, 5. You could have 4, 5. That's it. Length 3 sequences. You could have 1, 2, 3. 1, 2, 6. 1, 5, 6. 4, 5, 6. And then length 4, you can have 1, 2, 3, 4. That's it. You're sort of forced to have that. Length 5, again, you're sort of forced with that. And length 6, you're forced with this. So 1, 2, 3, 4, 5. So the green went from 1, 1, 1. Now it's jumped up to 5. The blues are 1, 1, 1, and another 1, 1, 1. 2, 4, 6, 8, 10, 12 of them. Now, curiouser and curiouser. So if I were to put these into, there's my M, there's my N, or capital N, I guess. 1, 2, 3, 4, 5, 6, 0, 1, 2. We had 1 all the way through, and then as soon as we hit 4, we got a few more. One, 2, 3, 4 for the blues. And then 5, 3, 4. Interesting. Very, very, very interesting. but I don't quite see a useful pattern. So I think this is where I went wrong. I don't think this is correct. But I don't want to keep going because I answered the question so long ago. So I leave this as a little challenge to you. You guys explore these M Eden sequences if you've been following along, if you're still around, obviously. And that's it for our, gosh, what was this? 2012, right? It's 2012. Yeah. So that's it for our 2012 paper. It's been a heck of a paper. You might be able to tell. I really liked this last question. I took sort of a computationally intensive way to do it, but if I'd had my wits about me, I might have been able to find that faster recursion way. And I like a question that keeps me thinking after I'm done the contest. Even if I'm just doing a math video and I don't have any stake in the contest, I like a good contest question that gets you thinking. Hopefully this one has gotten you thinking a bit too. Maybe. Anyway, so, you know, if you're looking for other Euclids, 2011 is the year before, 2013 the year after. I got plenty of Euclids sitting around on my channel, so feel free to pick one, and hopefully the questions are just as interesting as these have been. If you're looking for something a little lighter, but you still want to practice your writing skills, I would recommend the Hypatia. If you're looking for something about the same level of difficulty, maybe try the Canadian Senior Math Contest. The last question on that's pretty challenging too. But I will leave you to it. So I will see you in the future in another video. Until then, take care.